Okay, Claudia, take it away.
All right. Okay. Well, thank you everyone for being here today. We're going, Rosen Valchev is going to present this work on economic agents and imperfect problem solvers. And so Rosen is going to talk for 45 minutes and there'll be 15 minutes at the end for Q&A. If you have any questions as we go along, please use the Q&A function in Zoom and Cosmin will answer questions as we go. So and one last thing, there'll be a 15-minute meeting with the authors after this, and I'm going to put the Zoom link in here in just a second. So, all right, Rosen, take it away.
All right, thank you for having us, and thank you everyone for tuning in. So we are interested in a pretty basic friction of costly cognition, and you can tell that from the title. But the application is going to be about consumption, as was mentioned earlier. So let me start one by one. So first, our basic kind of motivational observation is that reasoning is costly. It kind of the right answer to tough questions does not arrive immediately, or kind of is not directly implied. So for example, just knowing all the axioms of set theory does not make it obvious that you know all the associated theorems of set theory, right? So one follows directly from the other one logically. So in some sense, there is no extra objective uncertainty, but we all know that reasoning through the axioms' implications, kind of drawing out the conclusions based on them, that's non-trivial. That's pretty hard work. So applying this to economic decision-making, the observation we want to make is that the cognitive cost of reasoning in terms of economic modeling would be equivalent to the idea of not knowing the optimal policy function. So the economic models we're all familiar with thinking about are, they have a representation as a mathematical maximization problem. Agents perfectly know the objective description of the environment. They see the maximization problem. Well, that directly implies what the optimal action is. And the typical model assumes that the agents also know that. This one implies directly by the other, so there's no cost in obtaining it. Now, we as economists know that actually there is a lot of non-trivial work that goes into figuring out the optimal action, especially in complex environments. But that's something that we struggle as economists, but we don't often let our agents struggle with. And that's what we're after here in this paper. We want to present a kind of formal framework, which is going to formalize the idea that computing the optimal action is difficult. It takes some cognitive cost, but the agents are resource optimal, meaning that they're going to act on their best perception of the optimal, and they're going to, follow some constrained optimality in how they decide to reason. So what is it all going to look like? Well, we're not going to take a stance on how exactly do people reason, right? So do I use heuristics? Do I do mental simulations? We're more interested in a bigger picture question. So we're going to abstract from the specific formulation of the reasoning process, and we're going to show that we can represent it mathematically as a signal extraction within a quadratic tracking framework. So the quadratic tracking framework is, I think, something that's going to be pretty familiar to us from the literature on costly information acquisition. We often used to seeing something like this is the objective function where I take some action C hat, and I'm trying to track some variable. In our case here, the variable I'm trying to track is the actual optimal action, which is given by the combination of the policy function C star and the state of the world YT. For simplicity, let me assume that Y is a scalar and also the action is also just one thing. We don't need to make these assumptions, but that's just going to be simple for explaining what we're after here. So what we're going to assume is that the agents know YT. So I know the state of the world. There's no issues there. What that means is that I know my preferences. I know, let's say, productivity. All these things, agents face no uncertainty. And the maximization problem of the agent, which is in front of them, they see it, is directly implying the policy function. We all know that. But at the same time, the policy function is not obvious, even though mathematically it's directly implied. And that's a concept that philosophy actually has struggled with, and also decision theory. What does it mean that we don't know all the logical implications of a given fact? They give it a term, meaning meaning that agents are not logically omniscient. And the way to model this is to essentially assume another layer of uncertainty, saying that, well, I know this fact, but me personally, I'm not sure whether it implies A or B. How do you model that? You assume there's subjective uncertainty about the implications. In terms of this economic application we have in mind, we're going to assume that the agents don't know the policy function C star. So I know why, but I face some objective uncertainty about C star. I don't know what is this optimal mapping between beliefs about the state and actions. And reasoning is going to be the process through which I learn about this unknown optimal C star, given all my knowledge about the objective description of the world. And in describing this reasoning as a signal extraction problem, we're going to kind of like follow or draw some insights from both decision theory and neuroscience in the following three ways. First, we're really after here the idea that reasoning is an internal deliberation. Sorry, excuse me one second. Reasoning is internal deliberation, meaning that it's fact-free. Agents are not acquiring any new information about the world. I'm not suddenly discovering that, you know, I make $5,000 more than what I thought I make. Instead, what I'm doing is this reasoning is helping me determine the consequences or the implications of my level of income. Agents are going to be resource rational, meaning that I realize that there's this cost-benefit trade-off. The more I reason, the better decision I'm going to take, and that's generally going to make me better off. But, you know, reasoning is also not free. It's tough to do. And lastly, we're also going to draw on some pretty recent evidence from neuroscience. Q&A is distracting me, but I shouldn't look there. Pretty recent evidence from neuroscience that the way the brain works, kind of like during decision making, the way the brain kind of accesses past memories and experiences that might be useful is similarity based, meaning that people don't tend to extrapolate from all kinds of things, but they're actually very good at compartmentalizing and saying, well, this particular problem over here looks like that other problem I faced in the past. That's the kind of memory I want to access. We're going to take all these three insights and we're going to put it together, and we're going to argue that this idea of reasoning can be described as if Bayesian non-parametric estimation of the unknown function C star is going to be both a very general but also a very tractable framework, and it's also going to be something that relates to the intersection of cognitive science and machine learning, which is also observed that, you know, when you're trying to write down mathematical formulations of reasoning systems for stuff like artificial intelligence, for example, kind of like this Bayesian way of going about it, kind of like this Bayesian decision maker based on estimating something is a pretty good mathematical formulation. It's convenient and also consistent with certain empirical evidence. Now, I'm going to describe this evidence, you know, kind of all the micro foundations of what we have in mind, but that's not really the most exciting part of the paper, I think, because at the end of the day, we want to know, okay, but what does that all mean about behavior? And there's some very interesting things that emerge. Number one, the similarity-based thinking and kind of the similarity-based evaluating of options is going to imply that state and history depend, going to imply that uncertainty, and the uncertainty that's facing the agent, is state and history dependent. What do we mean by that? We mean exactly that if for some reason the agent finds himself in a situation that looks similar to something they've experienced in the past, in mathematical formulation, that means a state of the world Y that's close to stuff that they've seen in the past, they've already reasoned about in the past. Well, in that familiar setting, they're going to feel pretty good about what they already know, and they're not going to deliberate anew. They're not going to deliberate much more again. And it's going to look like these guys are following some sort of like a behavioral heuristic. Maybe I shouldn't say behavioral. They're following a heuristic based on kind of past experiences. But if there's a big shock, moves into a new part of the state space, then suddenly you're going to realize, well, what I learned in the past is not so useful. And that's this idea of state and history dependent certainty. What I learned in the past is not so useful, well, let me deliberate again. So what do we have in mind? Well, think about a graduate student. they don't necessarily make very much money. You eat ramen for lunch every day for 4 or 5 years in grad school. Then you graduate, you get your assistant professor job, and suddenly you're like, wait a minute. This basic observation that ramen noodles for lunch makes a lot of sense in terms of my consumption profile. Well, maybe it's worth rethinking that. My situation now is much more difficult, and I am not willing to extrapolate very far away from it. And in terms of illustrating what does it mean within the framework of a quantitative economic model, we're going to follow this idea of an application to consumption savings choices. We're going to apply it to an otherwise standard Iagari model. And we're going to show you that the ergodic behavior is systematically different, even though they're from rational expectations. It's going to be systematically different from the standard model of full information, let's say, full information rational expectations. And the systematic difference is going to be both in the micro level behavior and some interesting macro implications. Let me try to give you a little bit of intuition. So what we're going to get on the micro level is high local MPCs, marginal propensities to consume, MPC. And that's going to be both for poor agents, but also for the very wealthy people who are very far away from any constraint. At the same time, there's also going to be large wealth heterogeneity. So how does it all work? It comes about due to crucial interaction between the evolution of the state and the reasoning choices of the agents. In particular, we're going to show you that there is this feedback between, I have some beliefs about what to do, but they have mistakes in them because my past reasoning signals are noisy. Well, these mistakes filter into how my state evolves. Because if I consume too much today, my wealth tomorrow is going to be low, and so on and so forth. So they filter into the state, and there's this feedback between choices and states and reasoning, and that can lead to these learning traps, where if at any given point in time, an agent has converged to a level of beliefs, kind of like a shape about the policy function that's relatively steep, in the sense that it's intersecting the permanent income hypothesis line from below. This generates a locally stable dynamic in wealth. Okay, why? Because if I'm in that situation and then I see a positive income shock, then I'm going to tend to consume too much, and my wealth's not going to increase. I keep it stable. But if the opposite situation, we get a negative income shock, then I'm going to save too much, again because my consumption function is quite steep. I'm going to save too much, and then I'm going to counteract the negative shock. Wealth remains stable. Well, but by wealth remaining stable, uncertainty is not going to fluctuate. I have no incentives to reason further. I'm going to keep behaving like that. So in some sense, these learning traps are only going to arise when the local MPCs are relatively high. When people have converged to a view of the world that implies that they should be pretty sensitive to small shocks to consumption. And that's like a deep reasoning implication. It has nothing to do with whether you're rich or poor. So it's going to apply throughout the wealth distribution. So rich people are going to have high MPCs. At the same time, the point of wealth, which becomes stable, is going to be different between people because they all receive idiosyncratic reasoning signals. So some people are going to be, I'm not sure we're lucky or unlucky, they're going to get signals to continuously save. And they tend to become very rich. Other people are going to get signals to consume and tend to become very poor. But at the end of the day, they're both going to settle somewhere around a stable point. But some are going to be rich on average, some are going to be poor on average. Yet both are going to display high local MPCs. Okay, so I think our contribution in a kind of like a very big picture sense can be summarized as a twofold contribution. On the one hand, we make this methodological contribution in providing a general portable modeling framework that's particularly useful for macro analysis in the sense that it's tractable. That's why it's useful for macro analysis, but still it's grounded in broad empirical insights on how human reasoning works. Now we have this framework, but the second contribution is also showing that it matters. It's going to matter both at the micro level. You're going to have very different MPC and wealth distribution behavior. And it's also going to matter at the macro level. And here the intuition is that all of this thing I told you about, what does the behavior look like at the ergodic steady state? What does it look like in normal times? Well, that's off the table if there's a big shock or if there's an uncertainty shock, because all of the agents are constraint optimal, and if you change the environment, you're going to change their behavior, and that's going to have macroeconomic implications, as I'm going to make clear later on. Okay, now we're related to a pretty long literature that's interested in sort of relaxing the very strong assumption of full rationality. There's a lot of work within this constraint optimal paradigm, looking at the idea that, well, maybe people perceive the state of the world in some imperfect way. Maybe I don't fully internalize that the interest rate is 2%, for example. We have this complementary but different interest in restricting how people kind of how people reason and how people interpret what does 2% interest rate mean about their optimal level of consumption. So in kind of the imperfect perception of the world modeling framework, you will typically have some incomplete information about the state, but then you apply the optimal policy function that maps it into actions. Instead, we say, well, I perfectly observe the state of the world, but I face some uncertainty about how to map it into actions. The process through which we reduce this uncertainty, which we call reasoning, is going to be grounded in a number of results I'm going to discuss in a little bit. The mathematical formalism has a lot to do with Bayesian statistics. And in terms of the application, I'm going to show you in order to argue that this friction actually matters for real stuff that we as macroeconomists are interested in. We're going to appeal to consumption savings models in the framework of incomplete markets. And in particular, we're going to have something to say about challenging features of the data, like high MPCs for the rich, very persistent hand-to-mouth status. Why are these very poor agents in the data not saving in our model? Because they don't know any better, but they're not suboptimal. They have their optimal belief. It just happens that the people who end up in the left tail of the distribution in the long run are the ones that end up getting a lot of high consumption signals. And as a result, also, we're going to have a lot of wealth inequality that's also very persistent, low social mobility. Okay, so I'm going to start by showing the general framework, and then we're going to the application. And when we're going to the framework, it's hard to follow sometimes these presentations. I'm going to try to keep it intuitive. And if you want to kind of keep something as an overarching narrative in mind, is that we want to be general, so it's portable across different economic models. So it's not only about consumption, and we want to be tractable. So how are we going to achieve that? Now, as I was saying earlier, kind of the uncertainty that our agents are facing are not about their economic environment. They understand what's the state of the world. They understand their preferences and any economic constraints and so on. What they don't know is this optimal policy function C star. As I said again previously, C star is, of course, mathematically implied by all this information I have already given them for free. But we're going to take seriously the idea that the fact that it's implied doesn't necessarily mean that it's obvious, right? So it's going to take some non-trivial effort to discover what exactly is the implied optimal C star. To model this mathematically would mean that the agents perceive the policy function C star as uncertain. And the key question that we as a modelers need to answer is, how do I model this uncertainty over the space of functions, and how do I model the information? Kind of like, how do we estimate it? So we have three guiding principles. First, we want to ground everything we say in some basic primitive evidence. And on that dimension, we're primarily going to appeal to some neuroscience results. It kind of says that, well, people tend to behave and kind of evaluate options in a way that looks like they consider specific past memories. They don't like form a parametric view of the world and then extrapolate globally out of it. They seem to be more basing behavior based on similarity with past actions and experiences. So this local similarity, that's going to be an important word for us. Then we also want the framework to be general. And what we mean by that is we don't want to impose an overly restrictive assumption on the prior on C star. For example, it's going to be too strong to just say it's linear from the get-go. And we also want to be tractable. We want to be something that eventually is going to allow us to put into a general equilibrium macroeconomic model. Taking all these three desiderata together, we're going to cast reasoning as non-parametric estimation of the unknown function C star. What does that mean? That means that the agents are going to be learning the C star via a non-parametric kernel regression. And again, that's an as-if representation. But let me explain them what actually happens mathematically. So they have this regression, and this, by the way, this equation over here, you should think of it as describing, in some sense, the prior beliefs of the agents. So the agents understand, okay, C star is a linear combination of basis functions phi k. These basis functions phi k are going to encode some prior beliefs of the agent about the basic characteristics of the function C star. The fundamental uncertainty is about the coefficients in these theta k's. It's about the coefficients theta k on each given basis function phi k. So theta k are the unknowns. So when you think about what does it mean that these guys don't know the optimal policy function, well, it means this. They don't know the coefficients theta k on whatever basis functions are describing the space that C star lives in. So we need to make a choice of the phis. And here's where we're going to appeal to both neuroscience and our desire to be general. So we don't want to make an overly restrictive assumption. You don't want to say, well, maybe the agent just thinks it's linear and that's it, because then it could be misspecified. If I just impose linearity on the phis, then there might be economic situations in which this is not true, and then I'm going to get strange behavior, but that's just because I'm overly restricting, kind of assuming my agents are stupid. So in order to make them general, and also appealing to this idea, again, these results of neuroscience, that there's some similarity-based thinking, the basis functions we're going to choose are Gaussian kernel functions, which all it means is just the probability density function of a Gaussian variable. So I can kind of see it's exponential. The state is y, and it has some mean. So each of these phi k's is characterized by just different mean. So we're splicing this space of functions by like a series of peaked, Gaussian kernels. They're just centered at different spots. And then the agent forms an approximation of C star as a linear combination of these things. This representation has a very long tradition based on non-parametric statistics because it's very flexible. It imposes no parametric restrictions. It's asymptotically unbiased. It's efficient. It has a great statistical properties. Interestingly, that Gaussian kernel is also exactly what the recent neuroscience evidence calls for. In fact, we saw the exact same mathematical representation of Gaussian kernels in some neuroscience studies that say, well, you know what, these brain processes here, I mean, the similarity-based accessing of some memories but not other memories, that really kind of looks like these Gaussian kernels. Okay, so we got these, and then we have the theta k's are the unknowns, but the theta k's, in some sense, are nuisance parameters. We as economists, we want to know something about behavior. What does it mean that the theta on one of the phi k's is high versus low? I want to know what does it mean about the beliefs over C star, the function itself. Thankfully, we can actually integrate the theta k's out. We need to assume some prior on them. We're going to assume that they're normal and IID. Then you can integrate them out. It turns out the C star has a closed form solution. The distribution for C star has a closed form solution. It's called the Gaussian process, which basically means that the joint distribution of the value of the function at any 2 points y and y prime is jointly normal, which is characterized by some mean function C hat 0. And here we have a degree of freedom because it kind of depends on what do we choose for the mean priors and the theta coefficients. But just we want to essentially tie our hands, eliminate that degree of freedom. So we're going to assume that the prior is centered around the truth. The prior is centered around C star. But the agents don't know that. They have some uncertainty. In the structure of that uncertainty, how do I perceive the function as uncertain around the mean, is given by this variance covariance function sigma hat 0, which, because of the Gaussian kernel assumptions, has a very nice closed form solution, which is basically says, the covariance between any 2 points, y and y prime, in particular the covariance under the prior of the value of the function between any 2 points, y and y prime, is decreasing in the distance. Is decreasing in distance between y and y prime. And this kind of shows you how information is local. Again, because if you can imagine that I'm splicing my space into these different things, and this is 1, 2, 3, and I can tell, okay, theta 1 is high. This is going to tell me something about the value of the function in the region of the state space where this very first phi1 function is active, but then it's not active in other places. That's like saying, as a graduate student, I figured out that eating ramen noodles is great for my budget. What does that mean for me as an assistant professor? Probably not too much, because it's the kind of like this, the part of the state space that I am in is just very different. Okay, so that's the prior uncertainty. How do I learn? I obtain these reasoning signals, which we call eta. They're going to be unbiased, so I get that it is eta centered around this, the true optimal action C star. So again, we're agnostic about how exactly do I learn any information about C star, but we're just saying, well, these guys sit down, think about their world, and we assume that they're, fairly smart. They get an unbiased estimate of what they should do. In terms of some previous literature, this is known as fact-free learning, because again, they're not learning anything new about the world. They're just drawing specific implications about themselves. In terms of tractability, Lemma 2 highlights that all of this relatively complicated machinery is actually very straightforward to work with. The time-t conditional beliefs about C star, based on all the information I have accumulated through these data points eta, just follows a recursion that looks fairly familiar. It's kind of like a common filter recursion, but just in the space of functions. Basically tells you that the estimate today depends on the estimate yesterday, which is then updated with a surprise in the signal. How much of a weight do I put on this new signal? It's going to depend on the covariance between where the kind of the values of the function, where the signal is centered, yt. I'm assuming I pull a signal at yt, and the state that I want to update about. Again, if I get a signal about what to do when I'm poor, that probably doesn't mean very much to me about what to do when I'm rich. In this picture, we kind of highlight this local updating, kind of local effect of information to make it very stark. This is an example of just one signal. This guy hasn't seen any other signal, just receives one signal. The signal is in the left graph, this open circle. And you see the blue line the blue line is the example how this non-parametrics works, and the red line is a parametric thing, but let's not go there. So the blue line just shows you that if I get that data point, then it has the strongest effect it has is right around the neighborhood of the signal itself. But then when I consider how do I update beliefs about the value of the function that points very far away, it's almost nothing. In turn, this kind of has direct implications about the uncertainty these guys are facing. Uncertainty is reduced the most right around where the signal is. Epsilon changes probably don't change my uncertainty very much. But if I face a big shock, then all bets are off. I kind of face an increased uncertainty again. I'm going to have to acquire new information. Now, how do I choose this information? How to choose how much information I want to acquire? Agents are going to be resource rational. They solve a quadratic tracking problem in terms of trying to stay as close as possible to the optimal in a quadratic sense. That implies that at any given point in time, I pick an action C hat that's exactly equal to my best perception of the unknown optimum. And I'm going to do all of that subject to an entropy cost. So this reasoning, these signals, they don't come for free. I have to sit down, take time out of my day, potentially really cause myself some mental grief to figure something out. And how costly it is also going to be parameterized by the marginal cost kappa of a unit of entropy. So if you put all this together, what is the optimal choice of reasoning? All I want to highlight here is the optimal choice of reasoning is going to be state and history dependent. Why? So the choice is really about the sigma eta, the variance in the signals. But as usual with entropy, we can express everything just basically about implied posterior variances. So what does the agent optimally want to do? At any given point in time, he wants to set his posterior variance equal to an optimal threshold kappa. He doesn't want to go any further below that because it's just not worth it given the information cost. And this is a familiar result from costly information acquisition models. What's different, however, is that when I compare the optimal threshold I want to reach to where do I start from at any given point in time, in our framework, the starting from is going to be state and history dependent. Why? Let me just go back to the pictures, the easiest way to see it. Because this Posterior variance here on the right-hand side is U-shaped. If I happen to be in a part of the world, like over here somewhere, close to where I have past information, uncertainty doesn't move very much. I'm pretty close to my optimal anyways, so I only get the imprecise signal. I don't spend much time thinking. Not spending much time thinking means what? It means that the weight I put on this new signal is very low, and instead I rely primarily in my behavior on past information. Now, of course, if I experience a big signal, state changes a lot, then it's going to be the reverse. This prior is not so important. The new signal is going to be very important. So you kind of see that actually people are going to have nonlinear changes in behavior. Okay, so that's basically what's happening in the background. What does it mean about something that we can put economic meaning to? What is this behavior? Let's think about the consumption savings application. And the reason we want to do that is particularly because there's going to be this feedback between the reasoning and endogenous data evolution. Again, if I get some reasoning signals that tell me to consume too much, that's going to tend to make me poorer than otherwise in the future. But that actually means that the state is moving around. Now, state is moving around from what I know, and I may have to reason again, and that there's a feedback there that I want to explain. Okay, what is the model? Is the simplest version of an IAGAR economy. Agents are basically receiving some exogenous income that's random. SIT is going to be IID both across time and agents and people. And all they do is choose the level of consumption. They carry around some level of assets, which they can invest at the rate that the interest rate are. They also face a borrowing limit, which means that assets cannot be negative. And because of our assumption that income shocks are IID, this means that there's only one state variable in this model, which this literature refers to as the cash on hand, which we define over here. So Y is the capitalized value of assets plus the new income. That's your cash on hand. And there's going to be this feedback I was telling you about, where reasoning beliefs are going to lead me to take an action, and that's going to affect my future reasoning, and that's going to affect the ergodic distribution of the behavior of this model. And before I go there, I just want to highlight that we want to be thinking about an equilibrium of this model. So we're going to close it. There's going to be a production function which takes aggregate k. Aggregate k is going to be the sum of everybody's assets, and it's just fixed to 1, so it's not very interesting. But this simple production function is going to allow us to figure out the equilibrium value of the interest rate and the wage. Okay, so let me illustrate the feedback between this reasoning and state evolution with the example of two agents who are exactly the same. They're going to receive the exact same sequence of income shock throughout their whole lives. They only differ in the reasoning signals that they receive in the very first period. And namely, one of these agents I'm going to call a consumer type, because he receives a positive error, so he's going to get a signal at time 1 that tells him to consume too much. And the other agent is going to be a saver type. He gets the opposite signal of consuming too little. So the consumer type is this blue line. So you see that guy got some signal to consume too much, and he updated his beliefs, and his updated belief about the policy function is the blue solid line on the left. The solid black line that's in between the blue and the red, that's this optimal C star. So you can kind of see that one agent's consuming too much, he had this positive error. One agent's consuming too little, he had the negative error in his signal. The signals that these guys receive, importantly, don't only affect their consumption today, which is going to be symmetrically dispersed around the optimal C star. Why symmetrically? Because their behavior is a combination of priors, but at time 1, they both have the exact same prior, and the signal. And the signal at time 1 is just differs because one is positive, one is negative. Now, the signals, however, don't only affect their behavior today, they also affect their estimate of the policy function, and that's something that they're going to carry forward in life with them. So the blue line, for example, the blue guy, the consumer thinks that consumption should be higher than optimal everywhere. Optimal, of course, he doesn't know what's the optimal. Only I, as the omniscient modeler, know what's the optimal line. We have to be careful about this here. These guys are not making any predictable mistakes. I just happen to know what the truth is because I'm simulating the model. So in some sense, I'm assuming that I have many more computational abilities than the agents inside the model. So the blue line, the guy that received the positive signal estimates consumption is high everywhere. The red line is low. And on the right-hand side, we again see this familiar U-shaped uncertainty that I kind of showed you earlier. The posterior variance after updating these two signals is actually exactly the same for both agents because the signal is in the same location. So both of them perceive low uncertainty right at white 1 and then increasing both to the left and to the right. Okay. Now, where do these guys differ? They're going to differ how they look next period. Because the blue line consumes too much. So the blue consumer consumes too much, so he's going to have low wealth next period. Red line consumes too little, he's going to have to tend to have high wealth next period. And it's particularly interesting to consider that feedback effect and how it interacts with an income shock. So here I'm plotting the example of a negative income shock. So at time 2, both of the agents receive an income that's lower than the mean. So that means actually they're going to have lower than expected wealth levels of Y2. Well, what does that mean? That means I'm kind of like shifting them both to the left, and the dotted red line over here kind of gives you the new position in the state space in terms of wealth of the saver type. And you can kind of see that the negative income shock is offsetting, it's counteracting the high savings rate, the counterfactual, or the wrongly high savings rate of the red line. So this guy would otherwise have increased his income or wealth. We're going to have increased his wealth levels, and that would have resulted in an increase in uncertainty. But the negative shock counteracts it, moves him back over here. So he actually perceives a very negligible change in uncertainty. On the other hand, the negative income shock is compounding the kind of change in the state of the poor agent, because the poor agent, sorry, not the poor, he's going to end up being poor, but I'm kind of running ahead of myself, is compounding the mistake of the consumer type. Now, the consumer consumed too much, so there is a negative drift in his assets. In addition to the negative drift in his assets, this negative shock moves his assets even lower than what they would otherwise have been, and that kind of causes a big increase in uncertainty to the blue agent. The negative shock kind of compounds this effect of the reasoning mistakes. The blue agent decides to not to revise estimates, but he basically decides, oh, I need to reason because I'm in a very different situation than what I'm used to. So he pulls a new signal and he gets a big revision in beliefs, which you can see by the fact that the solid blue line, which is the new conditional estimate at time 2, is quite different from the dotted line, which is the estimate he had at the end of time 1, or the prior that he enters the period with. So this guy revises beliefs. On average, he's going to revise them down because the new signals he draws are correctly centered around the truth. So he's going to, on average, discover that he was wrong. But the red guy is not going to discover he was wrong, at least not yet, because his what stays about the same. He's like, I'm not going to reason again. And here's this interaction where what we want to highlight is that the overconsumer, the guy who consumes too much, is only likely to discover that he was wrong following negative income shocks after his wealth falls, because positive income shocks are going to counteract his overconsumption. There's not going to be in a probabilistic sense. There's a low probability of his wealth starting going upwards. He's only likely to draw new signals once his wealth goes down to the left. As he gets new signals, he's correctly going to understand, oh, I was wrong. I'm consuming too much. But the local nature reasoning is going to mean that these new signals are primarily going to be most effective down here at the low level of consumptions. And he's going to retain his overestimate at the high level of consumption, a high level of the state, I'm sorry. Overestimate of consumption, high level of the state. So this local nature of uncertainty in reasoning is going to make me draw this steep line essentially between the two. So that's how high MPCs start getting formed. But when I move back into this area of the state space, I'm not going to revise beliefs anymore. I kind of retain that high consumption level. So over time, what happens with this guy as he simulates forward is that he establishes this high MPC, but importantly, it crosses this dashed dotted line, which I haven't mentioned before, which is the permanent income hypothesis line. When I have this upward crossing, this generates stable wealth dynamics. Because whenever I'm below that line, I have a positive drift in assets. So when I'm over here, my assets are going to be drifting this way on average. But if I'm above the line, then my assets are going to be drifting this way. So that actually becomes a local steady state for this guy. And that's how these agents are going to settle into steady states, where on the left side, they have a low estimate of consumption. On the right side, they have a high estimate of consumption. That's exactly what defines a steady state, essentially. And around that steady state, around that learning trap where they don't update beliefs anymore, because also once the state starts fluctuating around here, I don't perceive any more need to reduce uncertainty. So these guys are going to have a high MPC. Yeah.
Just one note. You've got about 5 minutes.
Yeah. Okay. Great.
Okay.
So these guys are going to have this high MPC exactly around their ergodic steady state. Now, the difference with the red agent is going to come into where that intersection, where that steady state level occurs. Because as we saw previously, the red guy is unlikely to revise beliefs given negative income shocks. He's actually going to start revising beliefs if they're positive income shocks that move him to the right. Eventually, he's also going to establish some upward crossing, and he's just happily going to stay there, fluctuating back and forth, exhibiting high MPC, so pretty sensitive, but at a high level of consumption. High level of wealth, high level of cash on hand. Okay, so we also want to put some numbers behind this qualitative result. We're going to parameterize the model, basically pulling on standard IGAR parameters. The reasoning parameters we're going to calibrate in a model consistent way, where essentially we solve a fixed point of simulating the model, drawing a sample of reasoning signals, and asking, oh, what would an econometrician estimate the distribution of these etas? What is the distribution of these etas came from? And that's exactly going to be the prior that we give the agents. And then kappa is in some sense the quantity, the magnitude of our reasoning friction. And one of the particular features I wanted to highlight over here of the model is that it explains why people kind of get stuck at a particular wealth level and then don't move away from it. Because once you get stuck somewhere where wealth starts fluctuating in a familiar region, you have no more reason to necessarily reason. One thing that this can explain is why people are hand to mouth. Why hand to mouth is a very persistent state. And the reason in our model is that these guys don't know any better in some sense. I mean, they have the optimal estimate conditional on their signals, but without seeing what signals everybody else has got, you don't know that you happen to have the signals that all have negative estimates, positive error, so overconsumption essentially. So we're going to keep kappa to exactly target the fact that the bottom 20% share of the US wealth distribution has exactly 0 assets. And that's something that our model is quite successful at fitting, but it's also, model is quite good at generating wealth inequality as a whole. In particular, there's going to be a whole large amount of agents that we target down here close to the borrowing constraint. But there is also a lot of rich people. Again, because some people, kind of the exact opposite of the hand to mouth, they got these signals to save a lot. So they're going to save over time, and eventually they're going to figure out, well, I'm saving too much. But once they figure it out, they're actually going to get stuck there. They're only going to figure it out at these higher levels of wealth, and they're going to stay there. In terms of numbers, the model is pretty good at generating Gini coefficient. So for example, the Gini coefficient there is very high, it's 0.77. The full information model is basically half of that. And we're somewhere in the middle at 58. And again, I want to highlight this is a very simple model. We have IID income shocks. It's quite surprising that we already get so much, I think. And then we also have this very persistent, so there's a lot of persistence in the wealth levels, low social mobility. And perhaps the most interesting thing about this low social mobility is why people stay poor. In particular, these hand to mouths are very persistent for us. Here we're going to compute the moment and kind of draw on some discussion of the Aguiar, Bills, and Bohr recent paper where they show that, look, in the data, the average future consumption growth of hand to mouth agents is very low. It's actually 0%. So this kind of shows that on average, no one's growing out to their constraint. And this is true in our model too. We basically are 0. But that's not true in the rational expectations model, because in the rational expectations model, people kind of being hand to mouth is a very unlucky occurrence that you quickly save out of. But that's not true here. People get stuck right at the constraint, again, because there's no way for them to know that they're not doing the right thing. They're doing the optimal estimate based on their previous reasoning signals. Now, as I explained, kind of a characteristic feature of what is the long-run belief of the edge is that the long-run belief of the edge is very steep. So you have high MPCs, and not only because of constraints, not only because there's a lot of hand-to-mouths, but also because these very rich people, the top 20% of assets have a mean MPC of 15%, which is 4 times bigger than the rational expectations model. And the very last thing I'm going to leave you with is that this is all great, but we should keep in mind that one nice feature I haven't emphasized is that this is the result of a constrained optimal behavior. And in particular, one thing I want to emphasize, there's a state-dependent uncertainty. So if I change the state too much, or maybe if I kind of shock uncertainty directly, people are going to change their behavior. In particular, one thing that people like to kind of point why MPCs are important for macroeconomists is because they're thought to amplify or propagate policy shocks. Cut taxes, and then we have an increase in aggregate demand because people have very high MPCs for some reason. Well, our model says that, yeah, people have high MPCs in normal times. That's kind of their ergodic behavior. But if you have too big of a shock, or if you decide to stimulate the economy after an uncertainty shock, which is what I plot over here, after an uncertainty shock, which destroys information, your stimulus might not be very successful, because look, the blue line is the model where there's stimulus with no uncertainty shock, and then a 1% increase in incomes is actually leads to 25 basis point increase in consumption. That's great. But if at the same time there's an uncertainty shock where a lot of information is destroyed, then people are not going to follow their business as usual behavior, which is a high MPC, but they're going to say, well, wait a minute, let me rethink again. Then everybody draws again from the C star. So everybody kind of starts looking at as a permanent income hypothesis consumer, and that greatly reduces the aggregate effects. Okay, well, thanks everyone for staying to the end. This is basically the paper. The conclusion, there's twofold contribution. One is methodological, and the other one is in the consumption savings application.
Great, thank you so much. A little depressing there on the end about fiscal stimulus. But it's good to have the model. All right, so we are going to go into the last 15 minutes, and anyone, I see one hand raised by Parntop, and I'm going to go ahead and unmute you. Let's see if I can do this. Oh, come on. As I am figuring out how, oh, I think your hand is raised. Okay, well, I'm going to go ahead and invite anyone who has a question to go ahead and raise your hand. You do that over in your participants place. And then also, it looks like, okay, it looks like y'all were kind of a quiet group. So there was one question in the chat, or not in the chat, in the Q&A that I'm not sure it looks like was answered. So I'll go ahead and ask that one. So there was a question from Christine, would insurance between agents worsen the belief traps? Why don't you all want to take that one first?
Yeah, thanks. This is an interesting question. I think it sort of depends. Obviously, it's going to depend what insurance we have in mind, but I'm interpreting it to mean that something makes like my own state less volatile, right? So I have these shocks that hit me, but there's also a safety net for some reason when I lose my job. And I think there's the intuition that the question implies is correct, that if there is something that stabilizes the state level of these agents, so let's say being the wealth, this is going to worsen the belief traps in the sense that it's going to be less likely that they escape them. Because these belief traps, we can always escape them, as my last example was showing them, if there's a big enough shock. But if there's also this insurance that kind of like ties everybody together to where they are, in addition, then it's going to be harder to escape them, yeah.
Right, okay. I still can't.
Claudia, may I
Yeah.
suggest one question that was raised, and I think sort of it may be on people's mind by Parantap Basu. He's asking, how does this approach differ from Sim's rational inattention, which is widely known. So I think people may have that in mind. And our answer is that it is very much similar conceptually. I think sort of initially when Sim sort of writes that, he does talk about actions, as uncertainty over action. But then slowly, sort of that literature started to focus more and more on attention to the state, and then given beliefs about the state, the mapping to the best, to the optimal action conditioned on those beliefs is just an aside. So that mapping is fully known by agents. There's no problem in them computing the mapping. Their problem in those applications is that they don't know the state. And so we want to change focus somewhat. We want to sort of push forward this observation that maybe we shouldn't give them so easily sort of that access to that mapping. And in fact, this is the whole kind of interest in a long bounded rationality literature and in neuroscience. And the contribution here is that we have proposed a tractable model of doing that, which is grounded in neuroscience.
All right. That's really also very helpful. Sorry, I'm having technical difficulties here. Let's see. Okay, to unmute.
Hello.
Sorry, just a sec. Okay, go ahead. Thanks.
Can
Sorry.
you hear me?
Yes, we can hear you.
Okay. Yeah, it's an interesting talk. In fact, one of the questions is already answered. And the other thing, I'm trying to understand the methodology, the modeling, because it is very hard to grasp that without looking at the paper, and it's a very short time also. But the way I understand that if I look at the Iagiri kind of framework, if I take some additive shock, some income shocks, that translates into a wealth distribution, which is an ergodic distribution of wealth, right? I think what you seem to be doing, you are just translating that income shock or bringing another kind of a signal. And that signal, there is a prior distribution of that, and that gives rise to some kind of wealth distribution, but it looks like it is just a simple transformation or reparameterization of Iagiri model by changing the income shock to some signal shock. Unless I've missed something, I don't see any clear updating or Bayesian rule that is coming prior, posterior, and how you are transforming the prior to posterior. I didn't get that. It looks like it is just a simple adaptation of Iagiri's model. Maybe I'm wrong, so I just wanted to clarify this.
So let me just go back for a second first to the conceptual framework, just to kind of highlight again where is the updating coming from. So one more back. Okay. So I mean, there's no, the income shock is not uncertain. I know what YT is, so I'm not updating any beliefs about YT. So that's what the rational attention model will do. You'll say, I don't know about what YT is. I'm going to get a signal on it, and then that's going to imply an action. Now, of course, because they assume that the agents know the exact optimal policy function, there's a one-to-one mapping between any beliefs about the state and an action, right? So they often cast the rational attention framework in terms of some distribution, conditional distribution of what am I supposed to do, see, given a belief about the state. At a very general level, it's similar. We also have a distribution of the agent, what he's supposed to do given the state, but the structure of the uncertainty is very different, because what's uncertain about us is this function, this C star function is what's uncertain, which in turn implies a particular distribution about it. And then you have, this is where the updating happens. This is kind of like my conditional belief about what's the mean of the function C hat T at any given point Y. So these guys, what these guys carry around in their heads is not just a conditional distribution over an unknown scalar like the level of income. What they carry around is a conditional distribution over the whole function C of how do I map any level of income to an action. So here, what I mean by this Y is just like an arbitrary Y. So for any arbitrary Y, the beliefs follow this recursion where the conditional belief of what to do at the level Y given information at time T is going to be, the previous information that I had at time T minus 1 plus the optimal Bayesian update based on the new signal that they get.
I see.
Right, now, when you apply that to the Iagiri model, right, so the Ys are exactly these income shocks and so on and so forth, but they do all that. They do all that update in the IGARI model again with the quadratic tracking problem. So what I was trying to show here, what this blue line is, this blue line is exactly the C hat TY, and it's a line, it's a function because the function of these y. So I'm showing you how they updated their beliefs for any possible state y. What could have been useful here actually also is to highlight where is the signal. So this guy actually got a signal somewhere over here. His action is here at the conditional expectation curve, but because the signal is noisy, he didn't update beliefs all the way to the signal, right? So it's a weighted average between the prior and the signal.
Yeah, but in that case, just a clarification that if I have this signal coming and if I keep updating, then eventually I should converge to a rational expectations equilibrium, right? But what is not? Why isn't that happening, right?
Very good. It's a very good question. So I was trying to show there's a selection in some sense into what part of the state space you're going to get pushed into. So if these guys were receiving random, if the state variable was randomly sampled across the whole state space, then yes, you're obviously going to converge to the optimal C star because the estimation is actually very efficient. But the Y is not randomly sampled. Y is endogenous. So it kind of depends on past mistakes. So in this sense, past mistakes become self-fulfilling. So this blue guy here has the past error in the signal was positive. He's consuming too much, which means that when you move one step forward, he tends to have low levels of consumption, kind of like his wealth on average is going to be falling downwards. So he's only going to draw new signals to get new data to update his beliefs only at lower levels of wealth. So what we mean by this is that the way that this guy's kind of like summary of data is going to look over time is that he's going to get some signals over here, and he's going to get some signals over here at the low levels. Now at the low, maybe I shouldn't put many signals. The important thing is that there was one signal that kind of started everything, and then wealth on average drifts down to the left. Then I'm going to draw signals which are correctly sampled from the truth, so they're going to be low down there. So then I'm going to update beliefs between that data point over here and that data point down there, and that's going to tell me something like this.
So it's not random draw. So signals are not randomly drawn.
No, not the signals. The signals are randomly drawn, but their location. Because so we always say that the signal that you receive, eta, is at whatever is my state level today, yt. So the signal itself is going to have a random error. So there's no tricks being played there. That's some random error. But where is the signal? Kind of depends on what you did in the past. Does that make sense?
Yeah, I have to see this. It is not clear to me that why I'm systematically deviating from rational expectations. At the end, we are not catching up. What is the fundamental reason? Can you precisely tell me what's going on?
Why don't we, sorry to interrupt, but this is a really good conversation. Maybe we can do this like in the small group chat, because we do have one more question. I want to make sure we get to
sorry to get
No, it's a great exchange. I just want to make sure, since we had one more hand up, which I think Frank, there we go. All right, Luigi, you should be unmuted now. Go ahead and ask your question.
Yes, just I was thinking about the persistency that you get for the hand-to-mouth agents. And like in the classical Ayagari framework, hand-to-mauth is a costly state, because one way to see it is that Euler equation might not hold with equality. So it's costly to stay there. And I don't see how they pay this cost in this framework, your kind of agent that is trying to guess what C star is. And if these could matter for the persistency result you get.
So there's kind of like two things there. Number one, so these guys are hurt by not being close to the optimal because they want to, you know, the objective function is they want to minimize this. I want to pick an action that's close to it. So we work directly in the space of policy functions or the value functions. So I know it's not like I have a low utility versus high utility, but this idea that I have lower high utility if I don't take the optimal action is captured by this quadratic loss. So you might think of it, for example, as a quadratic approximation to the value function. Okay, but it is important to highlight though that there's no state dependency in that cost, and that's an interesting extension we've thought about. So for example, you can think of this as kind of like the second derivative of the value function is as a constant, which we have removed because it's essentially a monotonic transformation. But we just do a value function approximation on a steady state. So kind of the cost of suboptimal action is the same, regardless of whether you're very poor or very rich. Now, we could have done something more sophisticated, which kind of takes into account that maybe, I think what you're trying to get at is the second derivative of the utility function at low levels of C, if there was some state dependence over here, and in how costly it is to me to make mistakes, then that's going to get to this idea that, well, maybe the guys stuck at the constraint actually, when they make the mistakes, even though they make a similar 1% mistake, let's say, in their action, they're hurt a little bit more than the guys that are very far out. They're very far out here. So we can definitely do that. We've considered it as an extension. Now, if we want to go that way, though, we should realize that we also need to think a little bit about what's the cost of this information they're acquiring. And I often think that the cost is perhaps the time spent thinking, the time doing things. And while the poor hand-to-mouths indeed have a very steep, very curved utility, they also tend to work a lot and don't have very much leisure. The leisure is very scarce too. So you probably wouldn't want to allocate too much to it thinking. So I tend to think that there's these two offsetting effects when you become poor. One, the curvature of the function is higher, so definitely mistakes hurt. But two, if the cost of thinking is related to how much time you have to take away from your leisure, then that's also increasing.
Thank you.
Okay, well, thank you. This was a really great discussion, or really great paper, lots of great questions. I am going to put in the chat, once again, the Zoom information for the small group. I'll leave this open for a little bit, and but again, thank you both to Rosen and Cosmin. This was very interesting. Thank you for everyone that came and participated. If you'd like to join the small session afterwards, go ahead and click through to the Zoom, and otherwise we will see you all next week. Thank you.
Thanks. And see some of you soon again. Cosmin, do you want to jump over to the other one? Should we both leave at the same time, or should we stay here for another minute?
You two can both go over. I'll keep this open. So if you click on the other.
Oh yeah, we can hear you, Parantap, but I think the idea is to go to this other room.
Yeah, I'm trying to see how I can get there.
There's the link in the chat.
Yeah, I already clicked that and to say, please wait for the host to start.
Oh, I guess I do have to. Sorry about that. I will click out of this one and get into that one. My bad.
I have a couple of questions to you. It's a very interesting talk, if you have time. Hello.
About having trouble unmuting and cutting off your conversation. It was a good one. So I will probably mute and let you all enjoy conversation.
Thank you. Thank you for letting me in. Can you hear me? Yeah, so see, this is a very interesting talk because I just started looking at this paper of Christopher Sims. It's a very difficult paper, but they also have a very similar consumption saving example in one of the papers on this. But anyway, that